So the university we are representing is Rutgers, New Brunswick, located in New Jersey. We are so excited to perform at the SUAS competition to showcase the progress we have made towards making an aircraft that can fly autonomously and creating an airdrop and imaging system that we can perform during the mission. If you take a look at the photo, this is our competition team from last year. So now we would like to take the time to introduce the members of our team from this year. So I will start off. My name is Jason Zambrano. I am the team lead and a hardware team lead. I've been RE Autonomous for 1.5 years, and I primarily focus on hardware and autopilot system.
My name is Evan Murray, and I am the airdrop subteam lead and backup safety pilot. I've been in RE Autonomous for 1 year, and I design various CAD modes for the dropping mechanism, and I assist in hardware.
Hello, my name is Osman Olasco. I'm the imaging sub-team lead. I've been with RE Autonomous for 1.5 years now, and I develop and train data sets through machine learning, and I assist with the electrical and programming aspects of airdrop.
Hi, my name is Carlos Moscoso. I'm a system tester. I've been in RE Autonomous for 6 months, and I help to develop tests to meet the competition goals.
Hello, everybody. I'm going to start off by explaining which requirements and criteria our team has strived to accomplish while designing our UAS. Our goal is to design a system that allows for easy setup, organized flight practice, and to ensure fast setup and on-time mission briefing. In addition, we'll establish a course of action for and alternative plans for action in case of failure, as well as effective communication between team members. All other parts of our goals are listed on this graph, and thank you.
So in regards to our design overview and design process, we splitted our entire team into different sub-teams in order to optimize workflow and expertise. So for each sub-team, we start off by asking fundamental questions that will lead to our goals for competition. So for example, for hardware, we ask, what type of aircraft do we use? What material should the aircraft be made of? And what components of the aircraft are optimal for this configuration? So after much discussion, we decided to go for a high aspect ratio wing. We decided that the material of our airplane is going to be made of foam, so it can be very lightweight, and we could optimize the weight for our payloads since this is a very payload heavy competition. And if you take a look at the photo, this is our configuration for the wiring of our hardware. So for each component, we do voltage and current rating tests to make sure that it is safe relative to one another. For autopilot, we ask what ground station to communicate to and what equipment will we use to ensure safe autonomous control. So we originally started off by using Q ground control, which is a very user-friendly system, very simple to use, but we found that it was not very helpful with troubleshooting errors that we've had. So instead, we transitioned to using Mission Planner, which gave us a lot more control of advanced parameters to help us solve these issues that we were having. For imaging, we ask what camera will have the range for this competition and how will we train the data sets that we have. The camera that we have is the FLIR Blackfly S, which has very high precision at high altitudes. And we train this data sets using a lot of images that we put together, using the alphanumeric characters that is going to be involved in the competition. And lastly, for airdrop, we ask what are the time, battery efficiency, weight, and stability trade-offs that we are willing to settle for. So for example, if we try to drop 5 water bottles at once, yes, that is going to save us a lot of time, but it's not going to be very weight efficient. And if we drop 1 bottle at a time, it's going to be the opposite. So what we chose to do was go with a horizontal stacked water bottle setup so that if we place that at the center of gravity, after all the components are on the plane, even if we drop 1 bottle, then the plane's center of gravity is not going to shift. So by doing this, we maximize stability, right? So if we have 2 vertical bottles and we drop 1, then that can actually shift the center of gravity and can lead to instability.
So for imaging, we decided to go with the FLIR Blackfly S 12.3 megapixel machine vision camera. This was fitted with a 12 megapixel lens. We went with this camera because it's able to produce high quality images from an altitude of 61 meters above ground level. From this altitude, we were able to set the resolution for 1 foot objects to be 36 pixels. This is sufficient for the object detection, localization, and classification systems. We are also utilizing the NVIDIA Jetson TX2, which is a power-efficient AI computing device to implement our unmanned machine learning applications. With the Jetson, we can control the camera with Python scripts to acquire images for the ODLC systems. Jetson can communicate with our team's central control servers to modify image parameters via the camera's Spinnaker SDK. So the initial plan for airdrop consisted of using a servo and a brake beam sensor. This was initially thought of as of our airdrop prototype, our airdrop idea, due to its simplicity. So the way it works is that the bottle on the bottom level would be placed in between a brake beam sensor, and when the bottle was released, the beam would be complete, which would send a signal to the servo, and allow the top bottle to be released to the bottom level to prepare for airdrop. Ultimately, we decided not to go with this idea due to its margin of possible errors. For example, the top bottle will be placed on a platform supported by a servo and a rod, which would cause too much stress to the servo and possibly drop too early. Also, when testing, any form of misalignment created false readings within the sensors. On top of that, we had to ensure that no additional light was present within the design, because that would also lead to false readings within the sensors. So as we can see in this video, whenever an object is present between the sensors, the servo moves, and when the object is removed, it goes back to its original position, which is the mechanism for the different layers for the bottles to be placed on.
Our current dropping mechanism is designed to hold 2 bottles at a time and made almost entirely out of black PLA, which makes it both lightweight and sturdy. There's also a total of 13 parts that make up this assembly, including 6 gears, a main body, 2 axles, and 2 parts that hold up the bottles steady during flight. Here is an animation that shows how this version of the dropping mechanism works. And yes. The dropping mechanism drops the bottle when it is prompted to by a program that uses information like wind speed, altitude, and characteristics of the water bottle, such as weight and color. On the right-hand side, we have kinematic equations that model the water bottle's trajectory through space once it's dropped from the drone. Also, there is a graph of the water bottle's altitude in relation to its downrange distance. It is observed that there is an exponential decrease in altitude after the payload is dropped. Payload will also be fitted with a small parachute that breaks its fall. We use RDF-90 telemetry radios from ground control stations to Pixhawks through autopilot data link operations at 900 megahertz. There is also an option for manual control to UAS through RX-8R Pro receiver and FR Sky transmitter operating at 2.4 gigahertz with a range of over 1.5 kilometers. Active in-flight information displayed from the Pixhawk GPS and battery in present time include altitude, receiver connection health, battery health, and servo motor output response.
So as mentioned earlier, we did decide to go for a high aspect ratio wing. And we thought that this was optimal for a competition that doesn't really require complex maneuvers like flips or anything that requires high rolling rates, because longer wings provide a higher moment of inertia, so it is going to provide more resistance. And this is important because it was stated that the highest wind current in this competition reached 24.2 miles per hour, so we want our plane to try to resist any high gusts of wind that might occur. And in the competition that requires a lot of payloads, we did want to have a plane that has a good amount of storage capacity in its fuselage, which this plane does have. So this is just to get more into the specifics of the electrical components that our plane consists of. At the heart of this configuration is the Pixhawk 6C, which I'm going to get more into on the next slide. So our Pixhawk is a microcontroller that is capable of running autopilot software, which is an open source unmanned vehicle software that allows for autonomous missions. We originally had the Pixhawk 4 series, but due to sensor issues that we've had in the past, we decided to upgrade to the Pixhawk 6C. So through the Pixhawk and the autopilot, we calibrate the GPS and compass. We can send our servos on there. We could hook up a receiver and calibrate a transmitter that corresponds to that receiver on autopilot. And because of this, we can obtain manual control at any point during our autopilot flights. We also have telemetry radios that are synced from our ground station to our aircraft, so we can send any type of signals that we want back and forth, such as return to landing in case of any emergency that happens.
So for the obstacle avoidance, we decided to use the LiDAR light rangefinder, which has an optical distance of 40 meters. It has a low power consumption and a small form factor. So the obstacle avoidance is due through the mission planner, where the LiDAR sensor is used as a proximity sensor. Then mission planner actually allowed us to set up the boundaries. So if anything comes within those boundaries, the plane will try to slide around it. This is the summary of some of the alternatives that we considered. For example, the original airdrop mechanism was prone to fatigue over time, and there was also a big delay when dropping the battles. We also moved from the Q ground control to mission planner because it provides a more advanced control of the plane. Another alternative was the use of a drone because of its hovering capabilities that give opportunity for higher degrees of control and precision for airdrop. However, it's more sensitive for unstable wings, has a high power draw and low flight time for a mission with a long runway. For this reason, we decided to use the fixed wing aircraft because it has a higher weight capacity for less power draw, which is really important for these competitions. We require 5 battles to be dropped. And also it offers more storage area for electrical components, more stability with its high aspect ratio. These tables provide some of the safety risk and the mitigations that we came across when doing the project. For example, we have the risk of overheating, which can damage some of the components, but this can be mitigated by maximizing the airflow inside the airplane. Another risk can be the loss of RC signal, which can cause the plane to crash. But we mitigated this by setting a safe flight mode. So when the signal is lost, the airplane will try to land safely.
The ODLC system is designed using convolutional neural networks with multitask machine learning due to its versatility. CNNs were implemented using Google's TensorFlow API. Our object detection model utilizes the single-shot multi-box detector, which was trained on 50,000 generated images containing 15 objects each. Through this training, the SSD learns the location of the bounding boxes of the objects and its associated classes. This produces very few false positives and detects objects with high confidence. For object classification, our model utilizes MobileNet V2, which was trained to simultaneously classify different characteristics of the object. These include the shape color, the alphanumeric, its color, and its orientation. The global cardinal position of the object is classified using telemetry information, which is collected through various sensors on the plane. This model was trained on over 2 million generated objects. Object localization is performed using telemetry data and the local positioning from the original image. These equations are used to localize the object. Here we have the equation for the angle of view, which is symmetric for the y direction using the sensor length. The position of the target relative to the plane's location is calculated in meters at the time the picture is taken. The latitude and longitude is calculated using Fourier series expansion, and the final geographical position of the target is determined by converting the position of the target's relative to the plane's location into latitude and longitude positions.
In order to ensure optimal performance, we conducted several tests. Firstly, we tested the system in various wind conditions. Secondly, we tested the system with different release heights and distances to assess its versatility. Thirdly, we tested the system in different environments to assess its ability to adapt to changing conditions. We also measure the time it takes for the payload to reach its target location to assess the system's speed and efficiency. To optimize performance, we can consider several things. Firstly, the system assumes no crosswind by approaching or moving away from the wind. Secondly, the distance is calculated in time increments of 0.005 seconds until the payload reaches a height of 0 meters. Our average aircraft takeoff time is 3.2 seconds. The autopilot has been tested on different complex waypoint configurations such as circle, tightly packed waypoints, height drops between waypoints, and sharp 90-degree turns. However, autopilot performance in autonomous takeoff and landing has not been performed yet, but we intend to test it before competition time. The RC receiver and telemetry radios have been tested at heights of 350 feet altitude and overall distances of 1,500 feet away from the safety pilot without any connectivity issues. On the right side, there is a chart that lists various aspects of our fixed-wing drone.
So for mission testing, what we do is we try to replicate the mission conditions as much as we can. So we head over to a large local RC field and we generate mock waypoints, drop locations, and obstacles. By doing this, gives us an estimate of autopilot and obstacle avoidance performance. It reveals any hardware, software connectivity issues that we might have, and it gives us the accuracy of drop locations. What we also do is we created a 550 millimeter quadcopter. We also gave this the ability to fly autonomously, and we also hooked it up to Mission Planner. So this way, while hardware sub-team could be working on the aircraft still, we could head over to this quadcopter and go ahead and test imaging on it. So that way it could optimize workflow and we don't have to wait for each sub-team to finish their tasks.
This is a video of the proof of flight, which includes autonomous flight and manual flight testing.
Thank you so much for your time. We are excited to perform at the SUAS competition in Maryland.